A Shavua says. A Valha says. Okay. So truth be told, A, B, C, D, E, and F, the roots. Which means, so if everyone is the root, then no one is. That's the colloquialism. If everyone is the head, then no one is. If everyone is in charge, then no one is. Point is that you could the reason why you said A is that the drawing alludes, it's trying to convince you of that, but it's not true. The drawing is arbitrary. The drawing of this graph that has A on top is arbitrary. You could similarly draw the same graph with B, C, D, E, or F on top. So the fact that A is there is a convenience, but I could have done D, and if you pick up the D and let everything else fall, it's the exact same graph, but now D is drawn on top. And you can do that with B, C, D, E, and F. Result being that the notion of a root is irrelevant in essence. Result being that the root is not unique in directed trees. So the main criteria is acyclic. But, as we just said above, in did I say directed? In undirected, I meant. But in directed trees, as we see above, and we'll move that over here, but one second. Acyclic does not suffice. And having a root is the significant criteria. That's that. Okay, good. So I just wanted to make you aware of that. Okay, Austin. No, there are no arrows because it's undirected. I just said. Okay. Now I'm talking about undirected. So undirected doesn't have arrows. But unless that's what you meant. That's correct. Oh, sorry. Okay, thank you, Austin. I'm sorry. I apologize. Thank you. All right, good. All right, any questions about that? So it's very interesting. No, it's how do you? Having been said that, now we can talk. Now we can go back into this discussion. All right, so there are three applications. No, one or two more definitions. All this is I need to distinguish something and say the following. Okay, now let's take the last graph. It applies to all of them, but since we're on this page, let's assume this last graph. In this last graph, the leaves. So this is oh boy. Okay. See, this is an official term. The problem becomes the leaves are only relevant to a root, but we just destroyed the notion of a root. All right. The leaves of a graph, the leaves of this tree are D, E, and F. Okay, note, this is not exactly true because since the root is not unique, the leaves which correspond to them cannot be unique as well. Wait a second. Yeah, that's true. Not every, I have to mention, is that true? Give me 1 second. Yes, as well. Although not every node, not every node of vertex in this last graph can be a leaf. The definition of a leaf, or leaves in plural, from the perspective of the root, are the nodes, vertices, that have out degree 0. So there's a notion of an in degree and out degree, which you should know from discrete math. In degree of a vertex V in degree is the number of edges that go into V, and the out degree of V are the number of edges that go out of V. Good. All right. Let's move this over. The leaf has no edges emanating from it. That vertex, okay. So that out degree of V is 0. In the above drawing, from the perspective of root A, then D, E, and F are the leaves, also known as the external or exterior nodes. The leaves, the data of these leaves, printed from left to right, or printed or listed, either way. From left to right, i.e. D, E, F, is called the frontier of the tree. All right, so it has to be relative to some root. Now, not every node, so which could be, it's under all circumstances, who could be a leaf. So E could be, D could be, F could be, but B, A, and C cannot. It depends. Well, that's the point. You see, if D is the root, then only E and F are. And same thing with E and F. If E is a root, then only D and F can be. And if F is, then only D and E can be. So from A's perspective, the leaves are D, E, and F. Okay, but it's really because we're imposing direction. We're assuming B goes to D, but D doesn't go to B. Otherwise, the out degree of D is the edge going from D to B. We're being a little loose. Simulates or emulates. Let me think. Assumes a little strong. Assumes that the edges from the root are direct. Assumes that even if the graph drawn is undirected. The point is that's the only way you can do it. Otherwise, it gets messed up. All right, enough said. This is discrete math, not for us. Okay. Yeah, okay. Shuhua asks, in the first tree, do both parents, can they point to the same child? Which is the first tree? What line number, Shuhua? Line 6 to 10? Anyway, bottom line is, two parents, okay, it can't be, because of the B criteria. You can't have two parents pointing to the, that's the dad problem. If I understand you correctly, how about the following? Watch this. Okay? This is a dag and not a tree. Yeah, because well, because the wonderful things he does. That's from what's that? Wizard of Oz. Anyway, ouch. It is a dag and not a tree. The because is not easy. The because is that B and D are the roots, and you only can have one root, so you're forced to say B and D are the roots, in which case there are two pathways from the root/roots to a leaf, and not a leaf, to the seed. The answer is no. Excellent question. It goes beyond us. This is a dag and not a tree because the root/roots, BT, if you want to call it that, have multiple pathways to a common descendant. But even if you don't want to call it roots, because it has multiple pathways to a common descendant. As to whether B and D are roots, see advanced graduate books. Excellent question. Excellent question. I wouldn't ask you this on an exam, but that is the reason. The B, if ignoring the root part, the main part of B is there's only one unique pathway to every descendant. And this has two pathways to a common descendant. So it's a dag, but not a tree. Okay? Shuhua, did I answer your question? I think that's what you're asking. If not, then I need more elaboration. Okay, excellent. Excellent point. Thank you for bringing that. That was an excellent. Thank you. Excellent point. Anyway, let's now get to the part we want. So here we go. Okay, well, one very last one. All nodes that cannot be leaves, although this is a bad definition, but all nodes that cannot be leaves are that cannot be or are not, but depending on your drawing, are termed internal or interior. Are termed internal or interior nodes. Say exterior, it's interior. If you say external, it's internal. All right. Now, good. All right, so now I can refer to these internal and externals, and now we could get finally to these guys, these trees. Good. All right, here we go. So in summary, a data tree, every node, internal and external, contain data to be processed. Okay, both. In an expression tree, only the external leaves, nodes, contain data to be processed. And the internal nodes are all operators. Sorry. In a decision tree, only the external leaf and nodes contain data to be processed, and the internal nodes are either are let me see, are weights or placeholders, as the case may be. So that way it pushes down the depth. Notice they have no data, just there to push down the tree level of the leaves. And that's done for priority to decide which leaf to go to. To the leaves, placeholders, to help an algorithm decide which data leaf to go to. All right, so let's try to give some examples of this, and let's see. So what would be a data? Okay, let me see. Hopefully, I know I'm drawing them. This file. I don't have it on this file. Great. All right, give me 1 second. 1 second, let me find it, because it'll save lots of time if I have a drawn example that we could do, which I should. Let me see, I should have it here. 1 second. Traversals, graphs, under graphs. Oh, maybe under graphs and trees. Okay, hopefully it's under graphs and trees. Oh, no. What? Oh, man. Hold on. Genetic programming? Maybe it's under genetic programming. Otherwise, if I have to do another one, I don't want to. Oh, man. Oh, here it is. I think this is it. Great. All right, I don't have Excel. I thought I could type it. Oh, shoot. Shoot. Is this mine? It is. So. All right. All right. Okay. I thought I had it drawn already. I'm sure I do. I just don't know where. Let me do it. Let me just do it already. Where are we? Let's see here. Oh, well, okay. It's not the greatest. The start. I'm sorry. 1 second. Where am I? Here we are. All right. So let's take this example. What I want to do is first data trees. Okay, first. Okay. So we're doing data trees. All right. So now let me move this over. Let's see if I can pull this off. And then we need this guy over here. All right. And okay, it's not the best drawing. It's not a terrible drawing. I've seen worse. That doesn't make you too confident, but okay. Yeah. All right. I know what to do. Hold on. Nice. All right. A little bit better. Not the best. D, E, F, G. Okay, let's do it this way. All right, so I want to go review with you the classic traversals. So there are 5 traversals of tree. Traversals means visiting all nodes and processing the data in the nodes. Traversals mean going through the tree graph and visiting the nodes. Sometimes all, sometimes some or all of the nodes. Okay, fine. And possibly, sometimes just visiting, and possibly processing the data contained within, which is the case here. All right, so we're going to assume that the data are these letters, okay, just to make life simple. Those are the names of the nodes as well as the data in the nodes. Okay, so there are 3 traversals, 3 classic traversals provided by base structures for trees, and 2 more provided for graphs. But since trees are graphs, we got 5 in total. Since trees are graphs, we have 5 in total. All right, so let's go through them. So the 3, in no particular order for trees, are what's called pre-order, in-order, and post-order. Okay, just to remind you of the orders. In pre-order, you process the node visited first, and afterwards you go left and right recursively. In order, you automatically go left, and then process the node, and then you go right. In post-order, You do you do a data. I'm sorry. You do left, right, and then the data. Okay. Note. There really should be 3 factorial equals 6 orders, which would include, let me see if I can do this, DRL, RDL, and RLD. But these are not considered because it's factorial, right? The DL and R could appear in 6 different ways, like we did in our heuristic mutation, and the 6-3 becomes 6. But these have been shown to be mirror images of the result obtained by, okay, but these latter 3, let me say it that way, but these latter 3 have been shown to be mirror results obtained by the above 3. Sorry. And are not considered new results. Anyway, the bottom line is no one does it for that reason, whether you like it or not. That's the official reason given. The point is you can get from any of these 3, you could get the result of the other 3, so no one considers them different. And here we go, pre-order. So I'm going to do this. You should know this already, so we're going to do this a little bit quickly. So we're going to start from the root and go through everybody, and the processing is simply printing. All right, so data means we go to A. After A, we go to the left. We entered B, so data recursively says B. And then you go to the left, which is D. So D, can you see me typing? You can. Okay, good. I was afraid you can't see me typing. So A, B, and D, and then data, and then you go left, right, there is none. So we pop up from the D. Having done the left of B, we go to the right of B, which is E. And then left, right, there is none. We're done with E. We're done with B, which is left and right. Now we go to A. So we already did the data and left of A. So we go to the right of A, which is C, being data. Then we go to the left of C, which is F, data F. Left, right, there is none. We go back up to C, which is the data and left of C. Then we go to the right of C, which is G. And then left, right, there is none. Go back up. C, we're done. A, we're done. And the result is A, B, D, E, C, F, G. All right, so that is the pre-order, yes, CFG. Yes, that's the pre-order traversal of G. Now, the in-order traversal says you go left, 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 which is D. Then you go, it has no left anymore, so D is first letter, the data. The right of D is none. So we go back up to B. We did the left of B, so now we do data B. Then we go to the right of B, which is E. Left, there is none, data E. We go to the right, there is none. Go back up to B, but we did the left data and right. Go back up to A, so we did the left of A. So now we're doing the data of A. Go to the right of A. So now we do the left of C, left of F. Left of F, there is none. So we go and do the data of F. Then we do the right of F, there is none. So we did the left of C. Now we do the data of C, which is C. Then you go to the right of C, which is G. Left, there is none. G is the data. Right, there is none. We've now done the data, the left data and right of G, the left data and right of C, and finally the left data and right of A. So DBE, A, F, C, G. Finally, post order. So post order goes left, left, left. So left of A, left of B, left of D, right of D, there is none. So the data of D is D. Then you did the left of B, now you do the right of B, which is E. Left of E, there is none. Right of E, there is none. So we do the data of E, which is E. Having done the left and right of B, we now do the data of B, and now that is the left of A. Now we do right of A, which goes to C, but that's not data. We now do left, left. So now the left of F, there is none. Right of F, there is none. So now we do the data of F, which is F, which is the right of C. Now the left of C. Now we do right of C, which is G, left, right, there is none, so we do the data of G. That is the right of C, so now we do the data of C. That is the right of A, and now we do the data of A, and that is the post-order traversal of this tree. Any questions on the pre-order, in-order, or post-order traversals of the tree? Again, this should have been taught to you and or data structures. Okay, now, from a graph point of view, graph point of view, these traversals are sometimes called searches. Okay, we'll call them searches, and there are two. Let's do the easier one. The easier is called BFS, which is breadth first search, which means level by level. Okay, and just let's do it. So A is on the first, then go to the next level, B, C is on the next, and D, E, F, and G, which is why I wrote it that way. One of them's got to be easy. A, B, C, D, E, F, G. Just go level by level. So from the terminology that we used above, descending from a node, to print the print or traverse slash print children in front, as if they are members of the frontier. Right? That's what we said, is believes from left to right. So that's what you're doing, level, but okay, that's fancy. But the point is, it's level by level. Okay, maybe you don't like that comment. All right, whatever. Let's do now depth first search. Depth first search. Depth first search, as I'll just say it already. So it turns out that depth first search equals pre-order applied to graphs. And the point, equals. I have to put a little mark here. Equals the pre-order applied to graphs, but keeps track of vertices slash nodes already visited. And in the literature, they actually call it visited. The array is visited. You implement the single array keeping track in order to prevent an infinite loop amongst the vertices, i.e. cycle. Right? Because if you keep going back and forth to each other, you have to say, no, don't descend, because we already did that. So it turns out that the depth first search is identical. It's the same idea. All right, so those 5 became 4. Pre-order, in-order, post-order, depth first search. Depth first search will be exactly the pre-order, but applied to graphs. All right, those are the traversals. Now, all these traversals, though, the luxury, let's call it that, the luxury of these traversals, is traversals of having so many, is that these all apply to data trees, but not necessarily to the others. For example, let's now do expression trees. Okay, so not all of these will apply. In fact, only in order will apply, the way it's conventionally done. Okay, so now let's take numbers. So 1, 3, 5, 7, and let's do multiply, let's do plus, and let's do minus. Okay, so here's our expression tree. Now let's evaluate it. So it's an in-order traversal. Okay, so the in-order traversal will be the following, and then we may have to add parentheses. Will be 1 plus 3, and the parentheses are just to make it easier to read, times 5 minus 7. That will be and you can verify this. Ignoring the parentheses, this will follow the in-order traversal that we did above. All right, well, I guess technically, if you want to be consistent, people would write it like this. Okay, so where the parentheses are based on the level that the node appears. But anyway, this mathematically, of course, is equal to